Okay, in this video, I want to go over the muddy points from Chapter 4, Measures of Spread. And one of the things that, I'll just do is kind of go through a quick example of how to calculate sum of squares, variance, and standard deviation. Just because, again, this is important formulas to be comfortable using and so on. And what I'm going to do is I'm going to do it using the computational formula, because that's the one that I think you should practice with. So let's say I had a set of scores. All right, so I'm just going to throw a group of scores together here. 6, 7, 7, 6, 5, and 8. Okay. So, actually, let's do this. I'm trying to think of, we'll just add a couple more here. Okay, so we've got 9 scores here. So we can see that we have an n of 9. Let's assume this is a sample. So if we assume this is a sample, that again is important to pay attention to, because when we're doing these calculations, we want to remember that there's a slight difference if you're working with a sample versus working with a population. So you look at the question, see what it's asking for. Now, in the question, it would say this is a sample of scores. You would have a lowercase n. And then when it asks for some things, it might ask you to calculate the variance, and it would call it the sample variance. And then would also ask you to calculate the sample standard deviation. So it would use all of the sample symbols. So what we have then is essentially 3 steps that we need to do. 3 calculations is probably the best way to think of it. The first one is we have to calculate sum of squares. Sum of squares for the computational formula is sum of x squared minus sum of x squared, and I put parentheses around that just so that you can designate that that is a sum of x, and then we're going to square the sum of x. Whereas this is a different thing, and this is something you need to be clear on, because otherwise this is going to mess you up. This is sum of x squared. So this is where you add up a bunch of x squareds. This you add up all the x's and then square that total. 2 very different things. And then we're going to divide by n here. And then eventually, once we calculate this, then we'll get to the variance calculation. And variance is the sum of squares from that previous step divided by, for the sample, n minus 1. And then once we calculate that, then we'll calculate the standard deviation, which is simply the square root of the variance that we just calculated in the previous step. So, to do this, when we're calculating this sum of squares formula, I'm going to put these in boxes so we can kind of identify and separate out the formulas here, is we need 3 things to calculate the sum of squares. We need a sum of x squared, we need a sum of x, and we need an n. Okay, so n is the easiest. We can count 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we know that that n is going to be 9. The next thing is I'm going to calculate the sum of x. Now, one of the things that's worth pointing out is here's a set of data. This is all of our scores, all 9 scores. Now notice that this is not a frequency table. If it was a frequency table, it would have an F column here to the right. But this is just a list of all the data. Okay, so in this case, and in this case only, to get sum of x, we just have to add up all 9 of the scores, which means we can add down the column. With a frequency table, you don't do that to get a sum of x. Remember, you multiply each x times the frequency. But in this case, it is just a listing of all the scores, so I'm going to add those up. And I'm going to use my calculator, and I would suggest you all use your calculator just because it makes mistakes less likely. So 6 plus 7 plus 7 plus 6 plus 5 plus 8 plus 5 plus 4 plus 5. I get a sum of x of 53. Now I'm going to double check that by doing it again. 6 plus 7 plus 7 plus 6 plus 5 plus 8 plus 5 plus 4 plus 5. 53. Okay, feeling pretty good. So now I create an x squared column. And that's where I'm going to take each score and square it. So I'll just do the first couple. I'll show you what I'm talking about. I'm going to take that 6 and square it. And that's 36. I'm going to take the 7 and square it. And that's 49. I'm just going to keep doing that for all of these scores. 49, 36, 25, 64, 25, 16, and 25. So this is a column of x's. To get a sum of x, we add up or sum all of the x's. Sum of x, 53. Now this is a column of x squareds. So if we sum up all of these x squareds or add them all up, that is a sum of x squared. Okay, so it's a sum of all the x squareds. So again, I'm going to use my calculator. 36 plus 49 plus 49 plus 36 plus 25 plus 64 plus 25 plus 16 plus 25. 325. Now, I'm going to double check that. 36 plus 49 plus 49 plus 36 plus 25 plus 64 plus 25 plus 16 plus 25. 325. Okay, I'm feeling pretty good about these numbers. What I will just say to you is when students make mistakes in this whole thing, this is probably the most common place they make a mistake, is squaring the numbers wrong. Like sometimes people will do 5 squared is 20 or 15 or 5. I mean, you never know. Or just adding these up and getting this number wrong. So if you get this number wrong, it's going to throw the sum of squares off, which is going to throw this variance off, which is going to throw the standard deviation off. So it's always kind of worth checking that. The next step, this is the next most common place to make a mistake, is just to plug the numbers in wrong or not have the right numbers. Now, when it comes to this calculation for sum of squares, you've got two numbers here in your table. You've got a smaller number and a bigger number. Okay, so there's our two numbers, 53 and 325. One way to try to remember it is just do the bigger number first and the smaller number goes in the numerator of the second part of the equation. But also just look at the symbols. This is sum of x squared. That's that symbol right there. So this is 325. And then minus. And then there's our sum of x. And that's inside the parentheses. So it's just sum of x. And that's why I put it inside the parentheses, so that it reminds me, this is that sum of x, 53, and then I'm going to square that. Okay, so 53 squared is 2809. And then I'm going to divide that by 9. Actually, I'll just show all the work. So that's, oops, and that should be a minus. So this is 325 minus 2809 over 9. 2809 divided by 9 is 312.11. So this is 325 minus 312.11 repeating. So I can subtract this 312.11 repeating from 325 and I get 12.88. Now it says negative just because I subtracted the backwards way, so I can get rid of that negative because it should be a positive, 325 minus 312.111, and we get 12.88 repeating. Okay, so there is my sum of squares. So remember that this is not the final result, but it is a step, and it's the hardest step. Okay, so it's the most complicated calculation that we do. It is a measure of spread, but it's not one that's easily interpreted as a descriptive statistic. Okay, so now what we do is we just simply plug that 12.88 into our variance formula. So variance is going to equal the 12.88. Now remember, that's still in my calculator. And it's 12.88 repeating over n minus 1. In my case, there's an n of 9 minus 1. So this is 12.88 repeating over 8. So now I just calc my 12.88, that's still in my calculator, divide by 8, and I get 1.61 repeating. So my variance is 1.611 repeating. Okay, so now that's my variance. Now that, again, is a very good and unbiased measure of variability. The problem is it's hard to interpret. What it means is these original scores, each of these deviate from the mean by about 1.61 points. So we could calculate our mean just to show. So our mean is sum of x over n. So it's 53 over 9. So 53 divided by 9 gives me 5.88 repeating. Okay, so that 6 deviates from that by about 0.22. The 7 deviates by about 0.88 or 1.88. What is it? 7 minus that? I want to know. Oops, 7 minus 5.888 is 1.11. Sorry, 1.11. So, oh, sorry. So we can essentially start to calculate the deviations here, and then what we would see is that then we would have to square those deviations, and if we squared all of them and averaged them, it would be 1.6. But that's not really useful. So you can see how it's conceptually, it's just a little bit confusing. And that's why we then plug this in to the standard deviation formula. So we get 1.611 repeating. And I'm just going to put that in here, 1.61111, and take the square root, and we get 1.269. And so that is our standard deviation. And so that's where, if we subtracted all of these scores from the mean of 5.88 and essentially averaged them, they should average out to about 1.2. So a lot of these some of these have deviations, like the 8 is 2.22 away from the mean. The 4 is 1.88 away from the mean. But like the 5 is only 0.88 away from the mean. The 6 is only 0.22 away from the mean. So the average deviation ends up being 1.269. So the one thing just to keep an eye out is that remember that this part here is the difference for a sample. Okay, so a sample is going to have n minus 1 in the denominator, but for the population, remember that the formula for variance for the population is sum of squares over n, and then the standard deviation is just the square root of that variance. Okay, so those are your formulas for population. Right. So that is all of the calculations. Now, a couple other things that came up. So I'm guessing some of you probably didn't have a lot of chance to work on the problem set yet. So, you might run into some of this. And again, you just have to be really careful. A couple things to really kind of watch for is there's, again, some sound issues. And I know it sounds weird, but sum of squares, SS, sounds a lot like sum of x squared. Those are not the same thing. Notice the sum of x squared actually is that. So that goes there. These are not the same thing. This is another concept. So try to remember. So what I'll do sometimes is I'll see people when they do a test or a problem set and they're asked to calculate the sum of squares, and then they've already done this table, and they'll say, well, isn't that what sum of squares is? Isn't that sum of squares right there? And they'll say 325. Part of it's because if you actually look at when we do this with the definitional formula, it actually shows up in the table. That's where in that column we have the far right column is where the sum of squares is. But this is specifically for the definitional formula because in that column, that far right column, we have all of the deviations that we found in this column squared. And we just sum up all of those deviations. I'm sorry, yeah, we sum up all the square deviations. So we take the deviations, we square them, and then we sum that up. So that's why sometimes people feel like, oh, that's where I get it. But when we do the computational formula, it is not that far right column. It is a result of the formula. So just kind of try to keep some of that straight. Other people talked a little bit about degrees of freedom was tricky, variance and inferential statistics, and the uses of standard deviation and variance was where I got confused. That has to do with a lot of this stuff at the end here. I wouldn't stress too much about that at this point. Partly because, well, it's not that wouldn't stress about it. It is not something that I test a whole lot, but it does help you to understand how to interpret a standard deviation. So one of the things, and this is just something to know, this is not, again, something I would test, but it's useful to know if you have a normal distribution. So this bell curve here is essentially what we would refer to as a normal distribution. If you have that, what we will find is 68% of the scores are within one standard deviation on either side of the mean. So, like, again, these could be IQ scores or SAT scores or GRE scores. And what we'll find is that 68% of the people will be between one standard deviation below the mean and one standard deviation above the mean. In other words, 2/3 of the people are pretty average. They're not that far from the mean. Not more than one deviation, one average deviation. So it's called the 68, 95, 99.7 rule because then we find that 95% of people, it's roughly 95%, are within two standard deviations of the mean. So it's the 68 between one plus between one standard deviation and two standard deviations. So plus this yellow part here. So we'll find that 95%, in other words, the vast, vast majority of people are no more than two standard deviations away from the mean. So to be way out here above two standard deviations, more than two standard deviations from the mean is a very rare thing. Happens less than 5% of the time. And so that's just one thing that we can kind of play around with. The other thing that they were talking about is in the muddy point problem was that the variance and how it applies to inferential statistics. Some of it comes down to that variability is going to help us understand how well a sample is reflective of the population that it came from. And so one of the ways is that variance, we talk about how variance kind of clouds the picture. So if there's a lot of variance going on in your study, meaning the people in your study, when you measure them, are very different from each other, something's going on. So you can think about it like on a test in our class. If, again, everyone scores very similarly to each other on exam one, what that meant is that there's not a lot of differences between each of you. And we can kind of see a pattern that people are actually learning this material and learning it pretty well and scoring pretty similar. Oh, I should say actually, if they all had high scores and a small variability. If they all have low scores and a small variability, again, students are not that different from each other, and I'm doing a terrible job of teaching the material. So, because all the students are scoring low and they're scoring very similarly to each other. Versus if there's a lot of variability, but scores are all over the place. So some students are doing really well, some are doing very poorly. That might be a little less on me because the students are different. Now, it could be that my teaching's not, working for some students, but it's a different interpretation. And part of it is that this variability can cloud the impact of any kind of treatment effect. So if you think of my teaching as a treatment effect, and there's a wide variability in students' performance, it's hard to really know what kind of effect my teaching had. But again, if everyone scores really high and has very little variability, everyone scores like in the 90s on this test, let's say, that means I did a really good job preparing you for the test, or the test maybe was super easy. And we can kind of see that. But again, if everyone's all over the place, it's harder to see that. part of the idea is to almost think of it like when you look at a screen or an old TV, you get snow on the TV, or newer, when we move to digital, you get more of this pixels and hex. It was like it just looks kind of weird. It's harder to see what you're looking at. Variability is like that. Variability kind of clouds the picture. So if I were to ask you, what's the mean for group A here? It's pretty easy. A lot of people can do it very quickly. I think immediately look at this and go, within a few seconds, say 44, because you see two scores at 44, one score above that, one score below that. And if you think about it as that teeter-totter, you have two scores at 44, one score right above it, one score right below it. That means that mean is going to have to be 44 for it to balance. But if I gave you sample B and ask you what the mean is, most people would say, well, they would take a long time to try to figure out. And in fact, they'd probably have to calculate it. But it's actually also 44. But it's harder to see initially because these scores are really varied. They're very different from each other. So there's more variance. It's clouding the picture, making it harder to see what's going on. So that's something that we're going to find that when we get to inferential statistics, variability becomes part of it. And it's because at this sort of almost it's like an analogy, it just clouds things. It makes things harder to predict or see. And part of the reason why, and we'll get way more into this as we kind of go through, is it has to do a lot with sampling error. So if there's a lot of variability in our study, then there's a greater chance for more sampling error. And sampling error is the thing that we have to wonder about. Is that why we're getting the result we're getting, rather than the treatment effect? That it has to do with who we sampled. So don't worry too much about that. This part is always just sort of preparing us for inferential statistics. So it's a little bit more conceptual and not something I'm testing directly quite yet. The last thing had to do with a couple things in terms of like it really goes back to that question of when we were on here and why do we use the n-1 for the sample, but not for the population? And again, not something I'm going to test you on, but the question came up as, why is it n-1? Why isn't it n- something else, and so on? And so if you haven't had a chance to watch it, I cover that very specifically in the lecture slides and the lecture videos. Is why do we use n-1? 3 reasons. The first has to do with this first issue, is that when we measure a sample, the sample comes from a population. The only reason we actually use samples is not to measure that sample itself. We use a sample to try to guess about that population that it comes from. Simply, what that means is, let's say I want to know, and we'll do it not with variability right now, we'll do it with the mean. What if I wanted to know the average, let's say, the average age of SCC students? Okay, so I want to know the average age. Well, I could measure all 8,000 currently enrolled students. Or I could take a sample, which would probably be a lot easier to do because the 8,000 students, they're probably not all going to respond. So I could sample maybe 100 students, or maybe to make my life easier, I'm going to sample the 25 of you in this class. Get your average age. You come from the population of all SCC students. Well, I can try to use your average age to estimate. And it's going to do an okay job because you actually did come from that population. But who knows how accurate it'll be, and there'll probably likely be some sampling error. So we always are using samples to answer questions about a population. If I instead, as the researcher, want to know what is the average age of this class, I can actually measure that. And in that case, I don't need to take a sample. I am measuring the entire population, and we call that a census. And so in that case, the mean is not a statistic. It is actually what we call a parameter, because it's an actual measure of the population. So we don't need statistics. We actually know. We know the average age of everybody in this class. But if I, again, want to know the average age of everyone in this class, but I don't have the opportunity to measure everybody, I could sample 5 people. and then try to guess at the average age. So the whole point of using samples is when a research question, it will decide the population. And if we don't have the ability to measure all the population, we'll take a sample and we'll use that to try to use that as an estimate. We can do that with variability too. So if I don't know the variability of a population, I can sample and take a sample from that population and measure its variability and then try to use that to estimate the population variability. The problem is that samples tend to underestimate. And the main way I can explain that is with this picture here is just simply that when we have a population, let's say it's normally distributed. So again, you want to remember this is a frequency graph. The y-axis, the height of this blue curve is the number of people. Okay, so we have more people right here in the middle because it's a high part of the curve. Up here, very few people because it's very low. Low over here on the left too. So let's say I randomly grab 10 people. There's a lot more people that I could randomly grab that are in the middle here. So I'm likely to get scores in here. And so probably when I sample it, my sample is not going to have as much variability. So if we just measured it in terms of range, look at how wide the range is for the population and how small it is for the sample. So that's the general idea. This doesn't mean that the sample is going to have less variability, but it tends to the vast majority of the times. So if we know that samples tend to underestimate, that's why we use n-1 in the denominator, because what that will do is it will increase the value of that sample variance. So if the sample is going to typically undercount how much variability there is, let's just make it a little bit bigger. And by dividing by a smaller number, it makes the result bigger. Because again, we're taking sum of squares and dividing by the number of people, but let's just take number of people minus 1. So we're dividing by a smaller number, that will increase the size. So that's one reason. So then I think it's reasonable to ask, well, why n-1? Why not n-2? That would make it even bigger, or so on. Well, the reason we do n-1 is because it's not that we're just let's artificially reduce the size. Let's reduce the size based on this concept called degrees of freedom. And this is, again, not something, if you watch the lecture videos, which again, you need to watch the lecture videos, is not something you're going to get tested on. But it's worth knowing because you're going to be calculating, and it's always kind of helpful to know why are we calculating this and what's it called? Why is it called degrees of freedom? Degrees of freedom refers to, the freedom side of it refers to how free the scores are to vary, meaning could the score be anything? And degrees is how many scores are free to vary. So the reason we use n-1 is because that actually reflects the degrees of freedom. So the idea, again, watch the video, it goes into this idea of, let's say we had a sample of 3 with a mean of 10. Basically, with that setup, 3 scores that have a mean of 10, by knowing that those 3 scores have a mean of 10, it puts a restriction on how many scores are free to vary. And it's one restriction, knowing that the mean is 10, and so it's n-1. And so I walk through kind of how that works, so watch that video. And then here's just another example. So if I just simply said pick 3 numbers, there's no restriction. All of the numbers are free to vary, so you have 0 restrictions, so the degrees of freedom is 3 minus 0, or all 3 numbers are free to vary. But if I say pick numbers that add up to 20, adding up to 20 puts a restriction on the data. It restricts how many degrees of freedom there are. It's one restriction, so it's the number of scores minus 1. So this one was n minus the number of restrictions. So it's n3 minus 0 restrictions, gives us 3 degrees of freedom. This one, same thing, it's n minus the number of restrictions. There's one restriction, so it's n minus 1, or 3 minus 1 in our case, n2. 2 of the scores are free to vary. And then if we said pick 3 numbers that add up to 20, but the first number must be 4, add up to 20 is one restriction. The first number must be 4 is a second restriction. So it's n minus the number of restrictions, n minus 2 restrictions, and because our n is 3, it's 3 minus 2, and 1 score is free to vary. Like for this one, if I said, pick the 3 numbers that add up to 20, what's the first number have to be? Has to be 4, because it's one of the restrictions. What's the second number? That is the only one that's free to vary. I could pick any number. I could pick 10, I could pick 42, I could pick 3,000, I could pick 2 billion, I could pick -7, I could pick 3.443572. Doesn't matter. that second score is free to vary. The third, so I got the second score now. First score has to be 4, second score can be whatever. Let's say it's a 10. First score is 4, second score is a 10. Third score is not free to vary. The first score and the third score were not free to vary. The first score had to be 4. Third score has to be whatever will allow those 3 numbers to add up to 20. And if that first score was 4, the second one I picked was 10, then it has to be a 6. But if that first score I picked was 100, then I say, okay, first number is 4, and second number is 100. That adds up to 104. How do I get to 20? So then I got to subtract something. So that third number must be a negative 84. Okay, so then we add 104 to negative 84 and you get 20. So that only one of the scores was free to vary there. So that's part of why we do n-1, because it reflects the degrees of freedom. So the other beauty with this is that by using degrees of freedom in the denominator, not only does it increase the score, it also increases it perfectly. And that's where we talk about it being an unbiased measure. Again, not something you have to memorize or be tested on, but just know that the n-1 works. And partly how we know it works is because when you take all the possible samples, the average of all the variances is average of all the sample variances is the population variance, just like the average of all the means is the population mean. And that's when we use n-1 in the denominator. So again, watch this video on that to get more detail. The last thing is just some people talked about in here about this kind of struggle understanding variance in terms of what it measures. That's very common. Most students can, eventually get a handle on how to measure it, but they don't understand what the number gives them. So what I'll just point out is that a lot of people talked about how the Desmos activities seem to help a little bit. And so one of the things is I want to kind of go through this really briefly because I have another video that when I grade it, I'm going to link to that video as well that just sort of explains this whole thing. But just to sort of set you up here, to remind you, I tell you in the Desmos activity, I'm thinking of a number between 0 and 100, and you're trying to guess that number. And every time you put a guess in, when you guess down here, it's going to show that number and it's going to give you feedback. So I'm going to make a guess of 44. Okay, so I submit that and it tells me 44 is too low. Okay, so now I'm going to replace the 44 with 88 and I'm going to submit that. Okay, now 88's too high. Okay, 70. Submit that. And 70 is also too high. Okay, how about 50? 50, submit that. Too low. All right, let's go with 60. 60, I submit that. Too low still. Okay, so it's somewhere between 60 and 70. Let's go 65. Oops, 65. There we go. 65. Also too low. How about 67? Too low? How about 69? Too high? Okay, it's 68. All right, so I guess I got it. All right, so now I can do that again and submit it, and boom. Okay, so I made all these guesses. Now, when we go to this next one, it shows me everybody else's first guess. Each dot is a different person in the class, everyone's third guess, and everyone's fifth guess. And one of the things that you can see is that first guesses are all over the place, which makes sense. No one has any idea. It can be anywhere between 0 and 100. Third guesses start to get a little better. All but 2 of the scores are actually above 50. Okay. And then by the time we're doing our fifth guess, you can see that people are really clustering around the actual number, which was 68. In fact, it looks like maybe a few people already have it. Now there's one person down here, and I want to kind of note that because I think one person might have been a little bit confused in terms of what they were doing. So it's kind of throwing things off a little bit. And so I just want to address that. But if we ignore that score, again, people are kind of coalescing right around the actual number, 68. So then it says, all right, here's two dot plots. Which one do you think is the fourth guess versus the seventh guess? Now, this one's hard because, again, this person, there was probably one person who might have not quite understood it. They guessed 7. All right. If we ignore that one and we asked which is the fourth guess and which is the seventh guess, most of you are going to figure out that basically the farther we get, the more likely we are to be accurate because we've gotten more and more feedback. And so this, I would argue, is our seventh guesses and this is our fourth guess. Now, in terms of how people guessed, it was pretty equal. Now, some of that has to do with when did you do this? Because normally I do this in class, and so everyone's doing it at the same time, so then we can see live results. Because some people go to this at different times with a fully online class, you might not have had a whole lot of feedback. So people were kind of all over the place, pretty much equally split between the two. And I think you could also make the argument that if that doesn't make sense for a 6th, 7th guess, is to be that far off. And so some people might have been thrown off by that as well. Now, standard deviation, as it says here, is that measure of spread. And so we can look at here, here's all of everyone's first guesses. It has a standard deviation of 21. Now remember, what does standard deviation measure? Average deviation from the mean. So if we look at these blue dots here, I'm going to guess, again, it goes from 0 to 100. I'm going to guess our average is probably somewhere like 48, 45 to 48. So then we could see how far each score is from 48 on average. So this score looks like it's almost an 80, 85. So that might be 32 points away from 48. That score looks like a 5. So that might be 43 points away from 48, and so on. And so, but there's some other ones that are right near 48. So they have deviations that are closer to 1 or maybe even a 0. But what is the average deviation? Turns out the average deviation is 21. Now, by the time we get to our third guesses, we're starting to coalesce again a little bit more up in the upper region near that 68, but we're still a good spread out. But notice that the standard deviation's gone down. People are getting closer. There's less deviation from the mean. Now, again, the mean is not the 68. The mean is whatever the average of everyone's guess is. And then by the time we get to the fifth guess, the standard deviation is now 6.2. Again, this standard deviation is taking into account this one kind of weird score. Again, they tend to be coalescing around 68. In fact, it looks like a lot of people have what I would argue is maybe a 0 deviation because they guessed 68 and the mean for everybody was 68. But the mean probably in this whole thing is not actually 68. It's probably closer to like 65 because that one score is going to pull the mean over. So even though those people got it right, their deviation might still be like a couple points away from the mean for the group. Now, what we can then do is guess what is the standard deviation here. And this one is just really hard to do because of this one weird outlier. If we didn't have that dot, I would say, and I would guess the average deviation here, again, ignore this dot here, I'm going to cover it up. And so if we're looking at that group of scores that are all right around 68, all the ones that are right on 68 have a 0 deviation. It looks like a couple scores have maybe a 1 deviation and maybe one or maybe 2 scores have 2 deviation. So average deviation is going to be a bunch of, so if you average it all up, it's a bunch of zeros, a couple 1s, and a couple 2s. So it's probably going to be like around a 1 or less than a 1, maybe a 0.8 average deviation. Now, with this one in here, we have to recognize that that's a deviation because the mean is going to be less than 68 now. And that's going to be a deviation close to, like that looks like, again, like a 5 or a 10. So that might, let's see, that's a 7. So let's say the mean here is 65. 7 deviates from 65 by 58 points. So that's a pretty big deviation to add into our average. So then the average deviation is going to be a little bit bigger. So that's making this whole thing a little bit harder. And again, I think it's because somebody got confused. Whereas this one, we can actually guess a little better. We look at the green dots and we try to figure out where the mean is. The mean's probably somewhere around here. I'm going to guess it's kind of right where this one of these 2 scores is here. And so then we can essentially look at, well, how much does every score deviate from that? Well, it looks like some of them are maybe as much as 5. These might be more like 7 or 8, maybe 9, 10. That one's maybe a 20-ish deviation. Those may be more closer to a 10 deviation. So what's the average deviation? Probably somewhere like an 8 or a 10, something like that. Okay. So then we can ask, and this is an important one, and then I'm going to stop for now because I do have the other video, but this is an important idea. Martina made a claim about the dot plots for her class. As we made more and more guesses, the standard deviation got closer and closer to 68. Without seeing the dot plots for her class, do you think she is correct? Whoops, I want to go back and look at what people said. Most people said yes. Okay, the answer is no. And so I want to look at the no answers. If Martina means that the value of the standard deviation got closer to 68, then she would be incorrect. However, the more guesses that were made, eventually to the final guess of 68, the standard deviation would decrease as everyone got closer to the final value. Yes, the standard deviation will get will get smaller as you get closer. And this Aria points out perfectly. Her wording is a little confusing. Wouldn't the standard deviation get closer to 0 the closer the guesses got to 68? Yes. So the way to think about this is that she says, as we made more and more guesses, the standard deviation got closer to 68. No. So there's two ways to say this. One is you could say, as we made more and more guesses, the mean got closer and closer to 68. Or everyone's guesses got closer and closer to 68. But the deviation is how much people deviate from the mean. And if the mean is 68 and a lot of people are guessing 68, you're going to get closer and closer to a standard deviation of 0. Okay, because they aren't deviating from the mean. And that's where it just asks you to sketch this. And I'm just curious how people did. So got it right. Max got it right. So if I just pull this one up, this is a distribution of scores that has a 0 deviation. And in fact, she actually chose 68. So she's putting them all at 68. And so if you look at all these scores, the mean is, let's say, 68. And all of those scores are 68. So how much do they deviate from the mean? 68 minus 68 is 0. Add up 0 and average them. The average deviation is 0. Okay, so that's important to know. So hopefully this helped a little bit to start to make a little bit more sense as far as this exercise. It can be a little confusing, but I also think it can be really helpful for people. So if you haven't, go back to it and maybe take a look at it again with everyone's scores in here. And thankfully, looks like this one, yep, everyone got this one right. The dot plots do have the same standard deviation. So by this point, everyone's getting that it doesn't matter where the dot plots are on the scale, it matters how spread out they are. So the mean is the middle part. It's the spread is the standard deviation. And so I can move a group of scores up and down and move them around. As long as I don't spread my hands any farther, the standard deviation isn't changing. Okay, so that